I'm Jacob Howard. I'm funded by the EUREKA program, and I'm working with Professor Omar Blaze in the Department of Physics, UCSB. And we're working on the investigation of corrugation modes as a mechanism for X-ray variability in black hole accretion disks. So let's get into it. First of all, I want to talk a little bit about black holes. Black holes look like that. Not just black, but there's a lot of plasma always being accreted onto the black holes, called the accretion disk. Now, all of this high energy plasma releases energy in forms of X-rays. Now, so far, this is not unexpected. They emit radiation, sort of like a neon sign emits visible light via the ionization of gas. However, what is unexpected is that these accretion disks don't just flicker like a campfire, but they actually have this sort of regular periodic blinking that is, so far, not well understood. So our idea is that we should look at these accretion disks to see what mechanisms might be responsible for this. The theory is that these X-ray pulses might be caused by trapped density waves in the accretion disk. So by the actual plasma being clumped together in certain places and moving about might be causing this. And in order to look into this theory, we use numerical simulations. So much like this here, we see these wave structures here, and we think that they might be these sort of density waves that we expect. And we want to compare these with mathematical prediction in accretion theory to see if that is indeed what's happening. And then, of course, we wish to compare it with observation. So here we have a light curve actually from a black hole system where there is a characteristic peak at around 67 Hertz. So that's the frequency at which it's blinking. So we want to take a look at how our simulation is varying and see if there's something comparable going on there. There it is. So first step is to search for some structure. Like we said, accretion disks are this hot ionized gas falling onto the black hole. However, instead of just seeing very chaotic structure, we see structures that are neat and organized in the form of waves. So first of all, to look at these patterns in the data, we use a mathematical method called Fourier analysis, which takes a time-dependent function such as how our density moves about over time and transforms it into a frequency-dependent function. In other words, we have difficult to resolve patterns, so it might be difficult to resolve any of the periodicities or what frequency at which these things are oscillating, and turns it into the Fourier transform can extract patterns and list them by frequency, so we know how much power is being produced at some frequency if there is indeed some structure. Secondly, we hope to develop an analytical model, which essentially means finding an equation for what's going on in these simulations and see if it's either something that's been explored before or perhaps there's something new going on analytically. And lastly, we hope to compare these to simulation data. So we want to look at our mathematical models, look at the simulation data, and see if indeed our analytical model is correct. So we want to collect clues directly from the simulation. Like I said, we take a time-dependent function and transform it into a frequency-dependent function via Fourier analysis. So in other words, we have some function some value that varies with time here, and as you can see, much more neatly distributed and viewable is our power as a function of frequency. So this tells us how much power is being produced at each frequency. Is it humming? Is it chaotic? What is going on? Is it structured? Is it regular? And we hope to use this information to build on existing theory. This involves first searching the literature for equations that might already exist that talk about what we're seeing and describe the trends that we're observing. And then we want to develop our own analytical results, whether that's building on something we've seen in the literature, if it's something directly from it, or if it's something completely new. That is the second step in our process. And lastly, we hope to compare it with analytical predictions from the simulation, compare these analytical predictions with our simulation data. So putting the analytical model back into the computer and letting it go and see what happens. Hopefully it lines up. And this sort of creates a cycle that continues until we find an analytical model that is acceptable and matches up adequately. So this requires probing the black hole, the virtual black hole, of course. And as we said, black holes don't just look like that, but they look like this. There's a lot of things always falling onto the black hole. that forms the accretion disk. But before we get into that, I want you to think about a record. So as many of you may know, records work by needles reading a two-dimensional, quasi-two-dimensional structure on the surface of the record, it's sending electrical pulses to the woofer, and the woofer makes these density waves in the air that you hear as sound. So we're sort of going backwards. In order to see if these density waves have any structure to them, we want to look more specifically at the two-dimensional structure of these accretion disks and see, because it's easier to look at the patterns in this dimension than it is in all three. So in order to do this, in our actual simulation of a black hole, we have several parameters. So this is our density here. More blue is less dense, more yellow is more dense. So we can see these clumps of density sort of moving out in the disk, which gave us an idea that something might be going on here in the first place. So our parameters are radius. We want to know which song to choose on the VLP in order to get the data. We want to choose where to drop our needle. For instance, if we drop our needle here and here at the same time, we're going to hear different things if we're at the same radius. And of course, it evolves in time. Our record is spinning. So firstly, we have our density as a function of 3 variables, which is difficult to work with, especially since Fourier analysis needs something that depends on time. So, time alone. So we freeze for a moment, and we look at one angular component, 0, which doesn't make an analytical difference as far as where you choose it, so far as you stay consistent. Now looking at this, we do see, in this simulation case here, some very clear structure. You can see here, as density is plotted, from lower to higher density, we get low, high, low, high, low, high, in what appears to be a very regular sort of pattern. So this is what we wanted to see, what we expected to see. But we want to be more rigorous with this. So we slice it where in a region that looks very periodic to the eye, and we get our density as a function of time as we initially wanted. And as we suspected, there is this regular periodicity visually. But of course, we want to run this through our Fourier analysis to see if there is indeed some structure, and if so, at what frequency is it ringing, so that we can compare it to the observational data that we have available to us. So when we do the Fourier analysis, we see that there is indeed a peak at low resolutions. But first of all, what's important is that at this radius, we have a very high peak in power produced at this specific frequency, which is what we would expect for this phenomenon if what is indeed going on is that it is this responsible. However, we had a hypothesis about this low resolution data. The hypothesis was that higher resolution data, which evolves more realistically in time, would more realistically model the effects of turbulence. Turbulence, as anyone who's worked with fluids before knows, gets in the way of lots of things. So in our low resolution data, we see this very, very nice periodic structure of dark light, dark light, dark light, dark light. However, in higher resolution simulations, it appears that this structure has been shredded only 20 minutes later in the simulation. But this fine structure has been shredded. So this findings indicates that although this structure might be present in the simulations and in the equations, we should also take into consideration the effects of turbulence, which is very capable at ripping these regular structures apart. Now, just to compare directly, because we want to be sure that we're not seeing any periodic structure there. Maybe it's just smaller and we can't see it quite as well. So where we have regular oscillations and we have a peak in the low resolution, our high resolution data is a little bit messier and the peak vanishes. So we were correct in some ways that turbulence might very well indeed shred these structures apart in untilted accretion disks like we're working with here. However, looking ahead, we hope to look at tilted accretion disks. And this is very important because there is a lot of evidence that the tilt of the accretion disk might actually be what is responsible for these modes, and they might survive whatever turbulence shredding is occurring there. So this is a very interesting avenue to explore next. Things that I have personally learned through this experience, which I think is very valuable to mention, the ability to visualize complicated data using creative plot techniques, which anyone in science can benefit from. Uses of Fourier analysis, which it's an extremely useful mathematical method. Highly recommend it. And anyone would. And how to search scientific literature efficiently and effectively, which is something that I was not very good at prior to this program. And for all of these very valuable skills I've learned, I have everyone here to thank. Hope it's okay I stole your pictures of Linda. I'm not stalking you, I promise.
I was good at mine.
Particularly Professor Omar Blaze for endless patience in explaining probably the same thing to me several times over. Chris White for providing the simulation data and writing the simulations. And of course, Sammy, Simone, and Tanit for all of the constructive criticism and putting this program together. Many thanks. And to all of you for all of your feedback as well. Much appreciated. So, thank you.